I'm ready to start if folks are ready. Can you hear me out there? Masha?
Hi, yes, I hear you.
Thank you, and I hear you. We're
Fortunatus.
continuing, please.
Yeah, Fortunatus, yes, I'm here.
Hi.
Good.
Fortunatus, where are you physically?
I'm in College of Staten Island.
Oh, okay. Well, pleasure to meet you. Okay.
All right.
So we
All right.
halfway through something that I call part 2 of NMR.
Huh?
Explaining and describing magic angle spinning spectra. And we were almost done, but I felt it was sort of an intense session, and I thought we did very well to have Anish just do problems with you instead for a little while yesterday. So I have a little smidge left of yesterday's lecture. So we talked about nested rotation frames. We talked about computing the FID. In other words, the time-dependent frequency. We talked about what is magic about the magic angle. Right now, the task in front of us is to compute the spectrum. And there's something cool, I think. Be alert for something cool. All right, so here's where we landed. We had this general expression of how to move from one frame to another, PAS to the lab through 2 rotations. That was a general expression for that. And as we truncated ourselves in both source and target frame, we only had to sum over 1m, which I designated m prime for the intermediate rotor fixed frame. And we did that, and we got this, which was the same as this, written out as explicitly as I can. Don't forget that you have to make a powder pattern. So this is an equation that would be good for 1 crystallite. Anybody have any feeling how many crystallites we have if we want to do a powder pattern? Just guess. Wide open guess. A million. Isn't it accuracy? I've seen this in the biochemistry and now in the physical averaging. Yeah, but we need to get our PhD done at some point. So how many do you want to do? It's very likely that if you have a few thousand, you will cover. Why? Because the line width can be imposed on each crystallite, and it could be of the order of a 10th of a ppm to 1 ppm. Our line widths aren't as good as solutions sometimes. So you wouldn't find the 1 ppm line width necessarily, but sometimes we're good with that. Yeah, so then it only takes about 100 objects to span the spectrum. So 1,000 should be sort of okay sampled, and 10,000 should be well sampled, right? But actually, there are algorithms that are smart where you realize the top half of the sphere is the same as the bottom half, and other things like that, so that you realize that with a couple of 100 crystallites, you sample things of interest in MAS. Would anybody here like to help me? This thing, I cannot turn it off, and it's not on. Thank you very much. So here's the equation we ended up with, and we need to do, as I said, a couple 100 crystallites. With, as somebody from there tell me, what is it that'll be different for each crystallite? As I go through each crystallite, what am I changing up here? Choose crystallite means choose the C terms. It's specifically what about the C terms?
No.
We dropped alpha, sadly. Beta is the most important thing you're choosing, but you're also choosing gamma. Okay? And gamma appears here as a phase. And yeah, I mean, you might have to choose alpha if you put it back in. This is a whole This is the full, you were right, you were right. Alpha is in that expression. Nobody's succeeding?
Yeah, it's that.
Poor Durant, she gets all the problems. All right, so I went back to uniaxial. I dropped the alpha and comments. If the angle is set correctly, the rotation is fast enough, dipolar anisotropy averages to 0. It's almost like we don't have the dipole coupling either. You guys don't have it in solution, we don't. The frequency gets averaged to the isotropic frequency, everything's solution line. And if the spin is slower, the frequency will modulate. Instantaneous frequency is, and at the end of each rotor cycle, it will come back and stop and pass through the original value. So if we sample only at the end of every rotor cycle, there seems to be hope to get a normal spectrum. Now, today, our task today. What we have is this, the top left, we have omega of t. One thing we could get out of that is accumulated phase. Accumulated phase, that sounds useful, but what specifically is it used for? We're going to elaborate why we want the accumulated phase, but in the thumbnail sketch here, accumulated phase as the explicit function of time directly gives you a free induction decay. And that one Fourier transform is your spectrum. Let's unpack that a little bit. So first, the accumulated phase. Let's just show that it's accessible to us. It should be the integral from t equals 0 or w time t prime equals 0 up to t equals t of the frequency. And the frequency is the delta omega that we have been studying as built off of a base of omega iso. But I can take omega iso back out again, just using a frame. I just remove it. So the isotropic phase accumulation would be omega iso of t, or I just sit in the isotropic expression, however you like to think about it. So we're just going to integrate this delta omega expression from the last slide. And that looked like this, except I could maybe drop these two terms if I like that approximation. So I integrate, and I'll let those two terms in for the moment, and here's what we get. We get terms that look like those amplitudes, and do you remember what those were, the amplitudes? They were geometric functions of the crystallite selection angles. And they scaled with delta, breadth of the tensor. So delta and then some geometric projection factor. Okay, that's what phi looks like. But when I do this integral, I pull out a formal factor of 1 over omega. That is important. That's going to come in. Okay, and then I have the omega r t type term, and I have the 2 omega r t type term. We're looking at sinusoids here for the simple reason that we integrated cosine. And if we retain the terms that relate to eta, the anisotropy, then we will end up with 2 cosine. That's a definite integral. I have to evaluate it at t equals t prime, equals 0, and t prime equals t. So then I'll have 8 very simple terms. Accumulated phase. I can pull out the ones in the yellow boxes if I want to simplify. I'm reminding you what C1 and C2 actually are. They scale with delta. Questions?
So we pick out those yellow terms only if they're long before symmetry.
If eta is not equal to 0. So that's a kind of map of where you are in this funny frame, the isotropic shift frame. Welcome. A picture that was hand drawn and undoubtedly wrong, but it's a picture. So this equation talks about sinusoidally varying if the argument that this function is phase, so we're in an XY plane. And we're saying if this would be the frame where I just sit there on my isotropic shift as a solution experiment would do, that's not what I'm doing. What I'm doing is I'm coming here and back here and here and here, sinusoidal. And it's clumsily drawn, but remember those other pictures we saw yesterday will have a 2 omega portion and a 1 omega, so it isn't supposed to look like a perfect sinusoid. How big are those excursions? They depend on delta over omega. And they depend on your crystalline selection data very strongly. So some of them don't do much. Some of them are all over the place. But at the end of a rotor cycle, they return where they started. So at the end of every rotor cycle, you're back here. So if you just want the isotropic shift, this is something Jay Shaker used to do a lot because he made more out of slow spinning spectra than anyone thought was possible. So he just sampled on periods. But otherwise, you oversample. This is kind of a weird FID. Wouldn't you agree? That each crystallite is doing that. We can't talk about like Lewis Hayes fast boys and slow boys. No, it's like everybody's doing crazy on that stuff. It's analogous to refocusing. This is what it's most similar to. It's a refocusing phenomenon that's entirely spatial. Now, if we spin fast enough, since the amplitude scales as 1 over omega, or rather delta over omega, then we can have a normal FID if we want. That's pretty good, like whatever you're going to sample at. But remember that 1 over x is a slow convergence. So hoping for that is, in some ways, a high wire act in terms of like how do you spin that fast. And it's a mechanical feat, but it's also a little bit of brute force because it's not 1 over omega squared, it's 1 over omega. Now, we have an FID. That thing that I just drew was the FID of like a particular crystal. Assumed to be uniaxial during sort of moderate MAS frequency. That was an FID. So we know how to get a spectrum from an FID, right? We're supposed to. What? I give you an FID, you can give me a. Yes. So, and you can do that in the reverse. I give you a spectrum, you can give me back the FID. But how do I formalize that? A normal FID, X and Y transverse components evolve sinusoidally, possibly decay exponentially overall as well, and that can be expressed in complex notation as follows. E to the I phase accumulation is cosine of phase accumulation plus I sine of phase accumulation. That is something you did a month ago. For a single fixed frequency, call it omega A, delta phi is just omega AT. It's pretty simple. And then we did this to it, right? So E to the I delta phi, or this doesn't need the delta. E to the I omega AT is cos omega AT plus phi sine omega AT. Forget the delta, please. So in this case, the Fourier transform, we saw this. It yields a singularity like a delta function at omega A. Or if you put exponential damping in as a reasonable assumption, it will lead to a Lorentzian line shape. You saw this before. And please review that if it looks unfamiliar. So I'm going to follow that as a roadmap. I'm going to say, yeah, I'm going to do the same thing, except it's not omega AT. It's the thing we calculated. Okay. So here's the accumulated phase, it's all of that. And you remember that if I want to exponentiate the sum of 2 objects or 2 numbers, then I can also take the product of their respective exponential. So I could take that times 0 versus the accumulation in this way. Sometimes that simplifies things. that's the FID, e to the I delta phi t. And it needs to be Fourier transform. But if you think about it, I know you have seen a function of this form. You're exponentiating a trigonometric function. What are we supposed to do? Where did you see this before? It's like a trigonometric of a trigonometric. So it's e to the I delta phi can be rewritten as sine and cosine. So what are we supposed to do with that? What do we do with all bad functions? Yeah, thank you for suggesting that, and it's a little bit of a exercise to the student because it's not really what I want to do with it. But I think it's the right answer if you've got nothing else. So the time-dependent part is weird, I say at the bottom. Would you like a Taylor series expansion? And actually, you could specifically use Maclaurin because if you think, okay, what are the arguments here? What's the variable, key variable? What are the leading terms? One of the hints that comes to mind eventually, hopefully, is that you could try to solve only one rotor period, and then the next rotor period is replicated. Okay, if it refocuses, it completely refocuses, and it has no memory of itself. It just still has the same Hamiltonian. Repeat. And you could impose the exponential decay independently. You can remove the isotropic. So you're literally starting at the same place at the beginning of every rotor. So now we're just trying to estimate a function over one rotor period. So clearly, the question is about the function of time. And so you start taking derivatives and so on and so forth. But convergence issues. We're in delta over omega, and it converges poorly. But it's not a terrible idea. I mean, you can get some things that way. But enter a better idea. We're going to do a series expansion in sinusoids. So you could do series expansions in different basis functions, and I think there should be a premium on basis functions that are actually orthogonal to each other. So if you choose normally behaving sinusoids as your basis function, they're not only orthogonal to each other, they're what we're used to in the spectrum. That's a beautiful basis function. So that's what we want. We want to rewrite this crazy thing as being a sum of normal sinusoids. It's a little different than the Taylor's idea, but it has some parallels. And how do we know how to do this? Well, frankly, I wouldn't have. Daniel Bernoulli is the Bernoulli of the Bernoulli effect. But it gets a little confusing because he's from a family with many, many mathematically accomplished Bernoullis. And his brothers. Can you imagine growing up with your uncle being the person who discovered and expounded on the number E? Like, that's a little intimidating. His father was one of the early inventors of the calculus, one of the people that we less celebrate, but you remember that thing about how it was independently discovered by several people. He and his father competed for the same prize in Paris, the university. And his father disowned him and threw him out of the house because he didn't like the competition. His father plagiarized his work and told him to study medicine. But what he did is the basis for the airplane wing, or carburetor for the human voice and most wind instruments. Like, he did some physics and some probability and statistics. And this is one of the things he developed as a tool on the way. It wasn't like, it was just a thing cast off as part of this problem. And then it was picked up by a astrophysicist, Bessel, afterwards and developed more. This is Bernoulli's work. Yeah.
When I became a scientist, my father said, I hope I'm not in an airplane when one of your buddies proves Bernoulli wrong.
Proves it wrong. Proves it wrong. Okay, so this is his expansion, and how's it work? So I don't like this. I want to rewrite it as some of these. Sine alpha. What is sine alpha here? So this is the problem we're solving, is that we have an exponent of a sine. Well, for us, we're talking about alpha being omega r t plus gamma. And what we're saying is I'd rather have just e to the omega r t plus gamma. I don't want e to the sine of that. So I'm going to have a series of harmonics in omega r t as being my solutions. And how much of each do I get? J, the best function. How many harmonics terms do I have to include? The whole series. You may have thought, like I certainly did, that because omega r kind of casts off a 2 omega r and an omega r term, that what I'm looking for in my spectrum is center band, first spinning sine band, second spinning sine band. It would have been very logical. But no, this is a series expansion and can go up to infinity. And that amplitude, J sub m, is not truncating to n equals 2. Nothing in this problem says that that's true. So the of x, that's the size of this amplitude modulation. So J is a function of not the accumulated phase, but of an amplitude of modulation. You might picture all of this like FM radio. Like you have a signal which is carried information in the amplitude of the signal and in the frequency deviations. Information is carried in both of those. And these kind of expansions are important in analysis of FM signal. Okay, so the amplitude of the oscillation and its argument, the accumulated phase. So J of x, and that's what we want. We want J for that harmonic as a function of its amplitude, and that's the problem we solved. This kind of series expansion shows up in a lot of physical problems in fluid flow, which is what it was known for, that have cylindrical coordinates. It's whenever cylindrical coordinates come up, this might come. So here's the functions. So x is unitless, and here, and you have J0, that'd be like a center band. You have J1, that's like a first spinning sideband pair. So if there's no amplitude to this oscillation, we only get a center band. If there's amplitude, the first spinning sideband comes in quickly, even with small amplitude. Kind of like sine of it. If you look at each subsequent harmonic, there's more of a sort of lag at x as they come in. And they converge very slowly, like the original problem converges very slowly, or die away very slowly. All right, so expansion in sinusoids, normal pure sine components with frequency. Yes, please.
We should go back to the previous slide. J1 will feature the first and the second sideband. Because for n equals 1, I take T2 over omega. And T2 is picking up 2 omega T plus 2 gamma.
Yes.
With the exponential.
Yeah.
The J1 of T2 over omega will
Come out of both
come
terms.
out in also the second sideband.
Yeah.
And so
Yeah.
that one. So J2 will become both the second and the fourth.
Mm-hmm. Mhm. Yeah, because I put this, but you always have to double it as well, that's what you're talking, yes. I'm just reinforcing what I've already said on the last slide. When you see alpha, think accumulated phase. When you see X, which I don't seem to have written, but I meant to, think the amplitude of the modulation. M takes any value, not just one or two. Amplitude of the components, those harmonics, is Jm of X. Oh yeah, I did say it, where X is the coefficient C over omega R. C1, C2, etc. So for our problem, X is unitless because it's the ratio, delta over omega. So this is a comb of spinning side bands in our spectrum, and we literally see them. There's no contribution anywhere else in the spectrum, just center band and side bands. But each chemically unique species will have multiple spectral features, not just the center band, the side bands also, and then clean in between. We have to do a powder pattern in this like everybody. It has to be integrated over representative crystal-like orientations. So the amplitudes, this is a representative term. We'll have several terms like this in our expression, but out of this term comes this series expansion. And this is sort of to your point, and so you'll get J0, J1, and so on and so forth out of this one term. And if we can assume X is small, like we're trying to spin fast, then J0 is large, J1 is small-ish, J2 is smaller. Okay, but that comes out of just one term. The reality is that we had the two terms, the point that you were raising. And so that would be like the product of the C1 term and the C2 term. Again, if you're adding them in the exponent, it's sometimes useful to break them apart. And so you'll take this series expansion times this series expansion. And so you get not only 1 and 2, but some of the differences in it. So the amplitude for the K spinning side band, if you sum all the terms, and it is just one crystallite, will be choose 2 such that it adds up to K. K equals N plus 2M. So A of K is choose 2, where again, K is N plus 2M. So you get a little bit of a complicated mapping, but not that bad. I want to say that this way of looking at the spinning side bands, this reapplication of Bernoulli and Bessel's work was primarily the work of Judith Hertzfeld, who had a very full career at Brandeis in biophysics and solid-state NMR, and was a wife and longtime collaborator of Bob Griffin, and had the pleasure of working with her on problems to do with bacteria redoxin. And I would say she had particular deep insights where math met the solid-state NMR, that's for sure. So we take on this approach to analyzing the spinning side bands, and it appears in many of the simulation routines. It's not the only way. Like you said, why don't we try a Taylor's, and that might be a better move now that fast spinning has gone in place. Maybe it's important to look back at it. there are other ways people have thought about this, but this was a real breakthrough to take this mathematics, and so that's the one I like to teach and just. So that takes us to.
Well, there's probably, if we look back to Bernoulli's and Bessel's papers, they probably started with an expansion in polynomials, and then some to give the Bessel function, which they then named. So they probably in fact did something with the Taylor series way back when. And now we have the shortcut thing.
Maybe, yeah. So looking back, here's part one of what we did. CSA and dipole are orientation dependent effects. In NMR, we talked about truncation at high field, and we talked about using Euler angles and spherical harmonics. That was last week. This week, part two was nested rotation frames, computing the FID, computing the spectrum, and what is magic about the magic angle. I remind you that you have turned in some homework here to turn in some more next week. This isn't about the grade. This is just about feedback, okay? Staying connected around how much of this is making sense. At a time, TBD, I don't know when. There's an even better topic coming up, which is what happens if you have pulse sequences during MAF? In other words, your spatial terms are time dependent. So your instantaneous frequency is time dependent. But now you're chasing that moving object with an RF pulse. And the RF pulse is also time dependent. And so what is the proper way to synchronize these two things? It's a big playground. And some very smart people have thought very deeply about it. And usually the goal is to select from a menu of physical effects, Hamiltonian terms that are actually true, but you effectively turn them on and off the way you want. The menu. You say, oh, no CSA today, I'll just have the dipole. No, not the heteroid included, I will the home included. So how do we do that? How do we select from that menu by recognizing the coincidence, time coincidence of the time dependence of the spatial term and the time dependence of the spin terms. So that's what we want to talk about. We start with a classic and relatively simple example, which has to do with using dipole couplings to move magnetization around instead of J. But that would probably take a full lecture and then a little bit, maybe more even for the homework. And then later on, and this is a question to the students, this is my last slide for today. There's all kinds of other solid state topics, and we like to get into them, but maybe they fit into the class only if the class has a kind of annex. So you're done, you get your grade, whatever, and then we have a few more topics in May. At the break or next week, just tell us what you think about that. Some of the topics I'm thinking about for solids. Decoupling, dynamics, quadrupoles, DND, paramagnetic systems, proton detection, and the practical experimental aspects came up a little bit. There's so much to say about that in solids, and I haven't put any of it really into this lecture. So you guys can think about that if that's interesting, and maybe we can put that towards the end or even after, hanging off the end of the class. This is just sort of like one more lecture to show how we think about effective Hamiltonians and average Hamiltonians and net action, but they on both time dependent. You just illustrate it with one basic example, and it's an everyday pulse. Specific implementation of cross polarization. So that's it. Other questions? Yeah.
Can you move back a slide or two?
Yeah.
Here, our A of K now is still written, isn't it, for a single crystal length?
Oh, of course.
So now there still has to be one more integration.
Always. Every single equation in this whole section, and it is not integrated analytically in practice. Some things you can, but not generally.
I mean, the separation, unfortunately, here isn't as clean as one might want because the crystallite dependence is. Oh, wait, I main and is
Initial,
the isotropic or
No.
the initial?
Okay, then I do.
yeah, you have some gamma.
Right, but inside the J's, yeah, there's not a separation, clean separation between the amplitude factors and the frequencies. Right. Or is there?
Well, the frequency, is your index. And the amplitude factor is X, the argument of the Bessel function.
I guess I'm really asking, there's no kind of sum rule of the Bessel function that lets you simplify the eventual integration. It already.
Integration is averaging, and we don't always do that. You lose the power of solid state NMR. If every time you think, what I really want to do is just forget about it, and stuff repeating, then, so I think there's a tendency, even in the rare problems where you do that. You're calling it integration, but I think what you're really wanting is an averaging. And we do most of our measurements as an average. It's a true thing. But here's some of the insights you might lose. We have blind spots. Some crystallites work better than others, and when you're troubleshooting, you may forget that. We have obviously opportunities to distinguish one orientation from another. If the question is either structural or dynamic, that can be very interesting. And many of those opportunities are unrealized right now, but I think they're very close. So it's good to have that explicitly reminded. But also, sometimes in an advanced pulse sequence, you get weird effects in the amplitudes of cross peaks or other things, because you have more than one anisotropic interaction at work. Like, let's say you're trying to do a dipolar coupling, but you also have a strong CSA on top of it. And so what you estimate as the dipole coupling can look very different on the first spinning side end and the center. Is that an artifact? Is that information? But it comes out of not thinking about the average, but thinking about the outer dependence explicitly. So I have a tendency, especially like in a class, to just leave it at that. Just, even if we could do an integral, it might be throwing away the baby with the bathwater a little bit. Other thoughts, questions? That'll come up again. This kind of question will come up again when we get to relaxation in solids. Do we want to just average to get a feel for things? Do we want to remind ourselves of an opportunity that it's angle dependent? Okay. Well, if other questions come up, otherwise,
another way of saying what you just saying is in solid state, the center band, which is what we get in solution, is perhaps the least interesting.
well, it's a working plane, right? That's where assignments happen. That's where resolution happens. That's a fingerprint and a working plane.
Hello.
Hello.
Except for the NC.
Hello.
Yeah.
Can you hear me?
I was wondering. You said that extra lectures may come up, and then student can ask for something regarding. You mentioned some stuff, including experimental aspect of structural calculation and few things.
Correct.
Like if somebody already has some NMR data, for example, but is finding it difficult on structural calculation, can somebody make such requests from? I mean, is it appropriate to? I mean, I don't know exactly what, but will it be nice for one to get some of these practical aspects on structural calculation?
Thank you. Okay, we'll take that as a request. And I know there are different levels, different amounts of background that different folks in the class have. So we'll try to think of something that will be flexible. Does that make sense?
Yes, thank you.
Recording in progress.
So now that that's it. Yeah, is this better? So now that you're all expert in tensors, we can go back to relaxation and solutions for a little bit. So what was the formula you're supposed to remember? For R2?
Was it variance times the correlation time?
Variance times the correlation time was the adiabatic part of relaxation. And we got at that from a simple model where we just had random fluctuations in the magnetic field along the z direction, so that would cause changes in the precession frequency of spins. And that was essentially an algebraic problem. We did some computer simulations, but then when we did the math, we just had algebra. Everything was scalar. Right? We did a Taylor series expansion of an exponential, but the argument to the exponential was just a number. So all we had to do was some relatively simple calculus and algebra. So that's convenient. Now you might recall the result of that was actually a little more complicated, a little more general. It was that R2 was the integral of the autocorrelation function for the fluctuations along the z-axis. But if the autocorrelation function decayed as a single exponential, then we knew how to do the integral, and then we got variance times correlation time. So we got a more general result and a nice simple heuristic result. Now, in reality, we don't just have fluctuations along z. There can be fluctuations in the magnetic fields in any direction. So I should write that I could have fluctuations in x, y, and z that are all time dependent. And now I have, even for a single spin, not even talking about more than one spin interacting, even for a single spin, I have a matrix equation. And now you're all getting to feel a little nervous. Oh no, not more matrices. So we could do the same thing. We could do everything that we did for the algebraic equation, except we have to keep the matrices around. And what's different about matrices than numbers when you do algebra? They don't commute with each other. So we would be doing the same thing, but the matrices don't commute, so we have to be very careful about order of operations. So we could do this. solve this problem for random fluctuations for a single spin. I did it once in a class in Brazil, and no one's ever asked to see that derivation again, because it turns out to be a lot of algebra for not all that much more insight. But as you've already seen, we can hide the matrices with symbols. And we're going to do that again here. We're going to represent the matrices by the symbols that we call operators. And we're going to manipulate the operators. And of course, anytime we're stuck, we can always go back to the matrices if we need to. But as I said before, humans like symbols more than matrices for some unknown evolutionary reason. Plus, of course, the matrices would quickly get very big when we go to 2 spins, right? The matrices, the operators are 4x4 matrices. And then if we talk about the interactions between the different elements, we very quickly get to very, very large matrices, whereas the symbols stay compact. So we're going to use operators and hide the matrices. And then the other thing that should be completely clear from man is we're extremely interested in NMR in rotational properties. So just as Ann expressed the tensors in terms of spherical harmonics, eventually we're going to do exactly the same thing, because not only are we interested in rotation around the z-axis, we're interested in tumbling, which again will be going to be described with spherical harmonics. So this theory that we'll develop is called the semi-classical theory. It's frequently given in the initials BWR theory for Bloch, Wengsness, and Redfield, who developed, or sometimes just called Redfield theory. It's semi-classical in the sense that, again, the lattice that we talked about that exchanges energy with the spin system, we treat as a classical heat bath. It has infinite heat capacity, can absorb and transfer any energy we need. In reality, it's a quantum mechanical entity, just like the spins. We could do a quantum mechanical treatment of the lattice, but it's way more complicated. So we won't. It's in the literature. But in all areas where you partition a quantum mechanical problem into a quantum mechanical part and a classical part, invariably something goes wrong. That then has to be patched in some way and then tested against experiment or full quantum calculations to make sure the patch was okay. And what we'll see is the semi-classical treatment doesn't predict that the spin system relaxes to Boltzmann equilibrium. It predicts that the spin system relaxes to equally populated energy levels. And we know that's wrong. We know Boltzmann equilibrium has to be populations that match the Boltzmann equilibrium. So we'll patch that eventually by saying we know that we have to go to Boltzmann equilibrium so that what we think was a derivation for relaxation of the density operator, in fact, was a theory for relaxation of the difference between the density operator and Boltzmann equilibrium. And that difference goes to 0. And it's just an ad hoc patch that, again, we can show is right experimentally, or a full quantum treatment can be done. There's another bit that has kind of come to be of some interest in the literature, that when BWR theory was developed, it appears that the originators of the theory recognized that it was going to be applicable to small degrees of polarization, small differences between alpha and beta state populations. And of course, 50 years ago, there were only small magnets. That was certainly true. Even now, for us in solution at 1.2 gigahertz, it's still a small population difference. But now there are methods of hyperpolarization that can generate quite high polarization levels in special cases. So there's renewed interest in what relaxation looks like in the high polarization rather than low polarization context. This falls, and it turns out that unconnected from NMR, a parallel theory had developed in statistical physics called Lindblad theory that applies to the high polarization case. So if you do a search in the literature, you'll now see there's a subfield of NMR talking about relaxation effects in the whole high polarization case using this Lindblad representation, which this is the last I'll say about it. Now, the good thing about doing the simple problem is we did the simple problem, which might be called a random phase model, in exactly the same steps that we're going to do the real problem. So everything we did is completely analogous. So what we're going to do is completely analogous. So we started with just writing down a precession equation where we had the Larmor frequency plus a fluctuating frequency along Z. And now we write the Liouville von Neumann equation, in which we have the time dependence of the density operator. It depends on the time-dependent Hamiltonian. We split that into an isotropic part that doesn't depend on time and a time-dependent part. We have the commutator. I don't like that. That's kind of ugly. So I invent a new symbol that's called the Liouvillean superoperator. And script L hat means take the commutator of everything that's on the right-hand side with respect to the Hamiltonian. And then I can write that as the sum of the Liouvillean superoperator for H naught and the Liouvillean superoperator for the fluctuations. And now you can see this last line looks exactly like this line as far as symbols go, except for a negative sign. I probably should have done the original calculation for n minus rather than n plus. It would look even more the same. But I have two equations that are isomorphous to each other, so I can clearly solve them by the same method. I just have to remember that L is not an algebraic number, it's a commutator of matrices. But again, anytime I get stuck on what that means, I just have to go back to the matrices and work out, maybe painfully, what the rules are. So what did we do first? In our simple problem, we switched to the rotating frame to hide the effects of omega naught. And now I want to switch to a frame and hide the effects of L naught. And in the literature, that's called the interaction frame transformation. But you can see it looks exactly the same. Here, I'm multiplied by a complex exponential. Here, I pre-operate by an exponential of L0. And I don't know what that means. That's now the exponential of a commutator acting on an operator, but I can expand in Taylor series and fiddle around for a while and discover that, lo and behold, this is this kind of sandwich operation that we've seen before. in which we have a unitary transformation of the density operator. How do I know this is unitary, by the way? Well, it turns out that the exponential of a Hermitian operator is unitary. And you can see that kind of trivially, e to the I h naught t times e to the minus I h naught t is just the identity, right? Because I can add the two exponentials together. In that case, they go to 0, e to the 0 is 1. So it's a useful fact. The exponential or Hermitian operator is unitary. I'm going to stick with this notation for a while. I just have to know this is what I really mean. Here's just the proof. Of course, knowing the answer, I can do a proof that this is right. I'll leave that for you to look at. So in the transformed frame, we ended up with the same equation, except omega naught is gone. And after we do the interaction frame transformation, we have the same equation, except L naught is gone. Again, the two equations look exactly the same. They're isomorphous to each other. So what did we do? We integrated the differential equation. We took an ensemble average. We expanded the exponential in Taylor series to second order, arguing that in the fast limit, the higher terms in the Taylor series would be negligible. We interchanged averaging and integration because they commute with each other. The first order term in the Taylor series expansion was 0 because we required that the average of the fluctuations go to 0. We put everything that survived averaging into omega naught, or now into H naught and L naught. And then we differentiated to get back to a differential equation. So we're just going to do everything exactly the same. And we ended up here with a differential equation that depended on the autocorrelation functions of the fluctuations along the z-axis. And now we just end up with a differential equation that depends on, or not a differential equation, an equation that depends on the autocorrelation function of L1 of the commutators of the fluctuating Hamiltonians. But again, formally, these look exactly the same, and they had to, because it was the same equation isomorphously. And then we wanted to do exactly the same things that we did before to turn this into a real differential equation. We said that we can replace m of t with m of 0 with m of t. So we'll replace sigma of t here of 0 with t, arguing we can work in a very small time step and then repeat that over and over again to get out the times we care about. And then here we said this autocorrelation function of the omega z's will go to 0 at very long times. We're going to make the same assumption here so that we can extend this integral to infinity, remembering then that that means we can't ask what's going on the time scale of the correlation time. We're only can ask what's happening on time scales longer than correlation time. That'll again be fine for rotational diffusion, whether it's fine for chemical exchange or other processes depends on the time scale. And if that's not a good assumption, then we need a new theory. But in the fast limit, we're only interested in times long compared to correlation time. So here we replace 0 by t. Here I replace 0 by t, but also I make my fix. I make the fix, then I know this differential equation has to go back to the Boltzmann equilibrium. So sigma 0 here is Boltzmann equilibrium, and I've subtracted it from sigma t. Now you might wonder why there's not a capital T here. but in to a very good approximation, the equilibrium density operator is the same in the interaction frame as the lab frame. I could have written a capital T there and then just done everything at the end. But as long as things like the J couplings are weak compared to the size of the static field, then the equilibrium density operator is the same. So I took a little bit of a shortcut. So here I've just then replaced sigma at time 0 by sigma at time t minus the equilibrium density operator. This problem didn't come up in our simple case, because our simple case we were talking about transverse relaxation. And at Boltzmann equilibrium, there is no transverse magnetization. So there was nothing to subtract off. But here, at Boltzmann equilibrium, there's Z magnetization, right? So we have to take that into account. And then we extended the upper end of the integral to infinity, again, on this coarse-grained time scale where we only care about time is much greater than tau c. And here's our result. Hopefully you see doing the problem you can understand algebraically first is a whole lot easier than trying to do this problem de novo. Particularly, the first 100 times you do it de novo, you don't recognize that you can replace the commutators with a new symbol. And if you do this keeping the commutators written out explicitly, one gets confused very quickly. It took me many students, generations of students suffered before I realized this was the right way to teach this. Now, if I put the commutators back in, then I just have the average of the double commutator to work out. And as it will turn out, we'll do some examples, but the Hamiltonians, we know there are things like chemical shift anisotropy and dipole coupling. So generations of students before you have worked out all the double commutators. So the problem set has you do one or two because it's good for you, but in reality, they've all been done unless you discover a new relaxation mechanism. They're already done. So this is called the master equation in the interaction frame. Right? We're still not in the lab frame. So before, we went back to the lab frame by undoing the rotating frame transformation. So now we have to undo the interaction frame transformation. But before we go on to that, let's see if there are questions about what we've done. It'd be good for you to go back and review then the first lecture on relaxation to refresh your memory of each of these steps and look at the computer simulations. They're really locked in your mind that, yes, we can solve this problem exactly the same way. Any questions online? Krishna?
Can you explain the second line, sir?
So I have L1 at T, right, and L1 at T prime. And they look there like they're multiplying each other, but remember, they're operators. So L1 of T prime acting on the density operator means the commutator of H1 T prime with sigma, and then L1 of T operating on all of that says take the commutator of L1 of T, of H1 of T with everything else. So operators, it doesn't mean multiply, it means operate on everything on the right-hand side. We have the commutator of a commutator of the density operator. And then I put the bar on top I just, instead of having the angle brackets, it's traditional to put the bar on top at this point in the literature. Yep.
Could you re-explain like how this equation incorporates the trend? So
Right, so they're going to be in whatever the Hamiltonian is. So they're in there, we haven't written down, we would have to go back, which probably happens shortly, right? And look at the Hamiltonian for the chemical shift anisotropy, for example. When we looked at it the first time, there were fluctuations that were represented by something multiplying IZ, and then there were fluctuations multiplying I plus and then I minus. And in our simple problem, we threw those away, the I plus and I minus terms, and now we're going to keep them. So they're in the Hamiltonian, but I don't see them until I actually write down the Hamiltonian. Now, to transform that, we have to find the derivative of sigma of t. And so I write down what it was. It was this transformation. I do the derivative with the chain rule. And this, so I have two terms. This first term is easy because I just recognize that as the commutator of H naught with sigma. So that just gives me back the normal evolution under the isotropic Hamiltonian, just like when I transform back from the rotating frame, omega naught reappeared. You'd be shocked when I transform back to the lab frame if I just didn't recover the evolution under H naught that I started with. I mean, if I didn't, you would say I did something wrong. Well, that part's easy. The second term, however, is a little more difficult. So the second term, I put in d sigma t dt is the master equation, right? That's what we just derived here. So here, this says I have to transform this differential. So I plugged in the master equation for the differential. And then the problem is, what does this mean? Well, remember, e to the I L naught t is one of these sandwiches. So I've written it out. Here's e to the minus I H naught t. And way over on the other side is e to the plus I H naught t. And then I'm going to play a usual game that I can always insert the identity operator any place I want. E to the I H naught t, e to the minus I H naught t is 1. So I can insert that. And what I'm trying to do is get everything into these kind of sandwich operators, so that hopefully I recognize what's going on if I have every term here look like one of these sandwiches. So this one on the end is easy then. This is just the back transformation of sigma t lab frame. So this part is easy, and I'm left with this part, which says, oh, and this first part here is also easy because the time indices are the same. This is just the transform of L1 of t back to the lab frame. And the tricky bit is here. When I'm left with, I have the unitary transformation with respect to t of something that depends on t prime. And that I've not encountered before. I just can't write that as L1 of t prime because the time variables are different. So this part is the hard part. Everything else was straightforward because where the time variables are the same, that's just my in and out of the interaction frame, just like in and out of the rotating frame. So I got 2 of the 3 problems done, and I have this one left over. Let me pause here for questions. And of course, I knew I wanted to put all these identity elements in the form of H naught, and because I've done the problem 100 times. I assure you, the first time I did it, I had no idea that that was a smart thing to do. It's always good to know the answer before you start a problem, but unfortunately, most of the time, we don't know the answer. Certainly, the people who invented the theory didn't know the answer when they started. Yep.
Did you need to make the assumption that the equilibrium density operator is when it's transformed is the same as the original theory? If you're changing back.
So if I had a T there for sigma naught, that transformation would just bring you back to sigma 0.
You didn't really.
I didn't need to do that. I should probably fix that. And the literature is never shown, I mean, never written as sigma T is 0, but formally it should be. And then you can see, just like sigma capital T of T transforms back to just sigma of T, sigma 0 of capital T would also just transform back directly. But formally it would be better if I put it in. Other questions? Any questions online? So probably 90% of the papers in textbooks do the remaining steps differently than I do them. And I think what we're going to do is the right way to do it. Now remember, we've assumed that the system is stationary. So the difference between T and T prime only depends on lag, on T prime minus tau, how far apart the 2 time points are. So I made that substitution here, and the question, and then the e to the and then while it looks like things depend on T, they don't really. And T is arbitrary in this at this point. So since I really just care about how the part of the transformation. Oh, I've done this backwards. Let me look, actually should be notes. So this part, we assume things are stationary. So then we have e to the h naught t, but that's the same as e to the h naught t prime plus tau, because t prime minus t is equal to tau. And now the bits here that depend on t prime do have the same time variable as t prime. So I can transform the t prime parts back to the lab frame and then replace t prime by t minus tau. But I'm left with these bits that depended on tau. So now I have the problem of how does, I'm back into the lab frame, that's great, but how does L1 of t minus tau transform under the unitary transformation e to the minus h naught tau? So I need to know something about the Hamiltonian here, how the properties of the Hamiltonian depend on tau. And right now, I don't know anything about the time dependence of the Hamiltonian. I've written everything very generally. But now I'm forced to know something to make progress. And here's where the tensor representation comes in. Because again, we're interested in rotations. And we're interested in then in how the density operator transforms under rotations due to the Hamiltonian. And that immediately makes us recognize that we should think of the Hamiltonian as expanded in some convenient functions that exhibit its rotational properties. And those, of course, are exactly the same rotations that Ann talked about in decomposing the tensor. So the notation maybe is pretty similar to Ann's. So A are the spin tensors.
That's T.
T for Ann. F are the spatial terms
That's R.
that contain all of the physical constants and the spherical harmonics. And then depending on whose text you follow, this -1 to the Q might be buried inside the R's, or it might be written explicitly. From this point on, there's all sorts of numerical factors that can be hidden in different terms that at the end give the same answer. But if you're looking at a paper, you have to figure out what terms the authors lump together. And I think here, we originally wrote this down following Richard Ernst's book, but for a long time, and the solution and solids had somewhat different notation. They've not completely converged on each other, but they've gotten closer.
Why they would want K instead of L? I'm not gonna fight over R.
Right.
That's like pretty arbitrary. Maybe F and A is nicer. I don't know.
Mhm.
But L, how can we give up
Mhm. I should probably look back in Ernst's book and make sure it was a K.
that?
That's not something I know.
Just the count.
Yes. Yes. So this is what you already know from Ann, that we have an expansion in terms of spin tensors and spatial tensors. And for us in solution, K is usually 0, 1, or 2, or Ann would say L is usually 0, 1, and 2. And the cases that she alluded to from very complicated things aren't likely to come up in solution NMR or biomolecules where you might have L of 3. And then, as she told you, this equation has the same form in the principal axis frame and the lab frame. It's just that if we're in the lab frame, the F's and the A's are in the lab frame representation. If we're in the principal axis frame, then the F's and A's are in the principal axis frame. And if we want to switch between the frames, we just have to do a transformation with these capital D matrices that you talk about, the Wigner matrices. So again, we have we're going to do the same sort of thing. It's going to be easier to describe the Hamiltonian in the principal axis frame, and then we'll do the transformation in the lab frame to take care of Cumulus. The only difference is going to be that now we have to keep all the terms, because we can't just get the term that went as 0, 0, because then we'd be dropping all these other effects of all these other fluctuations. Yeah, and then one other problem comes up is we also have to keep track of the fact that if we have if we, for example, have Q equals 0, Q here acts very much like a coherence that we've talked about in product operators. So Q equals 0, if we looked at a Hamiltonian, that could be coming from a Z operator in the Hamiltonian, but it also could be coming from, say, I plus S minus, a zero quantum term in the Hamiltonian. And if we have, say, nitrogen and hydrogen, Z operator has a frequency of 0 for rotation around Z, but zero quantum would have a frequency of omega I minus omega S, or omega S minus omega I, depending on which zero quantum term we had. And that's not necessarily 0 for a nitrogen and a hydrogen at 500 megahertz. What is omega H plus omega S? Well, the hydrogen frequency is 500 megahertz. What's the nitrogen frequency roughly? About a tenth of it. So what's omega H plus omega S? Pardon? What's omega S? What's the nitrogen frequency at 500? Pardon? 50. So what's omega I plus omega S? No, because gamma is negative.
Yeah.
So omega H plus omega S for the nitrogen is 450, and omega H minus omega S is 550. The carbon gamma is positive, so then that's what you think. Now, so you have to be very careful. In relaxation theory, the signs of the frequencies matter. Yeah.
So in our small magnet, that's a 475, right?
Mm-hmm.
So if we're doing nitrogen on that, it would drop down for 25.
Or 47.5, and then the omega H plus omega S would be 475 minus 47.5, whatever that is. So when you're doing calculations, if you get this wrong, obviously things are going to be wrong. And now the question becomes, what spin operator should we choose? What should the basis of operators be? You've already seen different bases of operators, right? We could have I plus, I minus, or IX, IY. So what should the basis be that's most convenient for us? And again, it's not necessarily so obvious, but we should choose the basis operators so that L naught acting on the basis operator is an eigen equation. So the commutator with the operator gives back a number, in this case a frequency, in the operator itself. Oh, of course, we got off track. The result of this difference between Z magnetization and, say, zero quantum magnetization is we can't just use the index Q. We need another index to keep those separate. We have to keep separate the parts of the Hamiltonian that come from IZ and the parts that come from I plus S minus. Unless the spins are degenerate, then we can lump them all together. So we need another index. It actually doesn't matter what that index is. I wrote it here as P, but I didn't put any limits because it depends on what the Hamiltonian is. Some Hamiltonians I need this, some I don't. And it's just keeping track of the difference between terms that have Q equal to 0, but actually have different eigenfrequencies. That the result of this calculation wouldn't always be 0, say, or some 0 quantum operator. So we could call P red, white, and green. It doesn't have any necessary mathematical formalism. But if we thought that we could give it a real meaning, and I don't remember in the notes whether I did it for these notes. If we did the formal way of building up the 2-spin operators from the single-spin operators with the direct product, there would be a formal way of assigning a number to P. But it's not so important. We just have to keep 0 quantity terms separate from Z terms. So this is convenient because if this is true, then it must be the exponential of L0 acting on a basis operator must just give back the exponential of the frequency. And I'm missing an I here. There should be an I up here in the exponent. Right? And again, you can prove that because we expand in Taylor series and do everything term by term. So you could say, I knew I wanted this. And to get this, I needed this. So that's how I decided to pick the spin operators. Again, knowing the answer in advance is good. So here I say, well, maybe we should assign them numbers. It's not important. This is what we all see. So maybe it makes sense to say if we have a product of spin operators, maybe we should call P equal to the coherence order of one of them. I may change my mind. Anyhow, here's to get to Chris's question, where all these come from. Here's the CSA Hamiltonian again. Before, we only took the part that depended on IZ. Now we need to take the part that depends on I plus and I minus and IZ. So then we have to do this transformation. So if L naught is dominated, or here, for each operator, we just need to know what its characteristic frequency is. So here, when I transform IZ, nothing happens to it, right? Because its characteristic frequency is 0. When I transform I minus, when I transform I plus, its characteristic frequency gives e to the minus I omega RFT. You have to look back at the notes and remind yourself that when you rotate I minus around Z, it picks up a minus phase factor. And similar, when I rotate I minus, it picks up a positive phase factor. And if I had 0 quantum frequency, 0 quantum operators, I plus S minus, I would pick up a phase factor that depended on the difference in the chemical shifts. So then I can write in the interaction frame. How are we doing on time? Okay, it'll be just another couple minutes. In the interaction frame then, my equation, expansion for the Hamiltonian, just has these extra phase factors that were accrued when I switched into the interaction frame from the lab frame. So I've chosen wisely the operator basis to get a very simple looking equation in the transport frame. And implicitly, I transform the F's into the interaction frame, but I don't need for what I'm going to do to indicate that. Of course, everything would be transformed into the interaction frame. Now, here's where we were. And now I want to plug in what I've currently learned with this last bit. And when I do then this transformation and plug in the expansion, I end up with just getting all of these outs, all of these new phase factors. So this bit of the transformation that I wasn't sure how to do. Right? The F's are now depend on t plus tau. The rotation, the effect of the exponential of the Hamiltonian acted on the spins, didn't act on the spatial terms. Those are just numbers. They come out of the sandwich operator. So I transformed the spin parts of the Hamiltonian in this expression. But as we saw, we just pick up these complex exponentials. So that's pretty nice. So then we can write very quickly this full expression. Now, at this point, we want to do a bunch of simplifications, and that will take us a little while, so I think we'll leave that for next time. So you should review these first 21 slides and then go back and compare to when we did it the simple algebraic part. And if you're happy by Wednesday, on how we got to this point, the rest is actually just kind of numerology. This is the conceptual part. Any questions online? Good. Again, review these first 21 slides. And this is really the heart of the results.
Goes with the podium. Thank you.
Oh, all right. Sorry.